Okay, Organic Chemistry 2330. Today we're going to start the chapter on carboxylic acids. It's chapter 13. We'll have 3 videos in this series talking about all the different interesting things that carboxylic acids do. Okay, so first thing we have to do is talk about carboxylic acid and what the structure is. This is a continuation of the aldehydes and ketones we started in the last chapter, where we have a carbonyl as the core of the functionality. In the carboxylic acids, though, we add an electron-rich oxygen and a hydrogen to the system. What this does is this gives us our generalized system that can be written either with the electrons on it to help us see what's happening in the reaction, or in 2 shorter forms with COOH, or occasionally CO2H. All of these represent the carboxylic acid and has that acidic functionality. If we have an aliphatic carboxylic acid, we can write it in a general form with an R group as our aliphatic group, followed by the COOH. If we have an aromatic group, we tend to use the AR, indicating that we have a benzene or some other aromatic system there. Okay? So when we start talking about naming carboxylic acids, we typically take the name for the longest parent chain that the carboxylic acid is in, drop the E and add oic acid at the end. For example, if you would have hexane, you would say hexanoic acid. Okay, so you drop the E, add oic acid. Occasionally, you'll have a double bond in that system. You have to drop the A portion of that and keep the E so that we can signify that you have a double bond. For example, if you had butene and a carboxylic acid on it, you would call it butanoic acid. So you'd have the E in it. Okay. So in this case here, we have a nice simple one right here. We have butanoic acid. That's 1 carbon, 2 carbons, 3 carbons, and 4 carbons. Notice the carbon of the carboxylic acid, the carbonyl carboxylic acid, is in the number of carbons in the main chain. Also, it is also the number 1 carbon in the chain. So we always number from that carbonyl carbon 1, 2, 3, 4 from there. That way we have on this, we have a single methyl substituent. So it's 3-methyl butanoic acid because we have a total of 4 carbons. In this case here, we have a phenyl group as a substituent, and we have an alkene. So we have 1 carbon, 2 carbons, 3 carbons. So that gives us pentene. So it's pentanoic acid, and we have a substituent on that 3 carbon. So it's 3-phenyl propionic acid. And because this group and this group are trans to each other, we have the full name as trans 3-phenyl propionic acid. Okay, this also is called cinnamonic acid as the common name. Okay. So up to now, we've been adding new and functional groups. We started with naming alcohols as our parent, and then the ketones and aldehydes became our parents. Well, carboxylic acid takes precedent of all other groups. So we have to name it for the carboxylic acid. So if we look at this first one here, we have carbon 1, 2, 3, 4, 5, and 6. So we have hexanoic acid right here, and we have a hydroxyl group on that 5 carbon. So it's 5-hydroxyhexanoic acid. When we have this other carbon here, we have to again start right here at the carboxylic acid carbonyl and have 1, 2, 3, 4. So that would make it butanoic acid. Therefore, we have 4-amino butanoic acid. Okay, and remember, aldehydes and ketones are just below carboxylic acids, and whenever we have an aldehyde or ketone with a carboxylic acid, we have to use the prefix oxo. And so we have oxo plus the carbon it's on. So in this case, we have 1, 2, 3, 4, 5, 6. So that makes it hexanoic acid because we have 6 carbons. And then we have that ketone on our 5 carbon, so we call it 5-oxohexanoic acid. Okay, it's very common also to have dicarboxylic acids. They typically have a carboxylic acid at the end of long chains, and these are called dioic acids because you have 2 carboxylic acids. So when we name these, you take the carbons in the chains, basically from carbonyl all the way to carbonyl. That's our parent chain. So in the case of 2 carbons here, that would be ethane. So we'd call it ethane dioic acid. That would be its IUPAC name. Here we have 1, 2, 3. So that would be propane dioic acid, and here we have 4, 5, and 6. So we would just add the parent name plus dioic acid. Now they also have common names associated them, and so when we just have the 2 carbons in it, it's oxalic acid, malonic acid, succinic acid, glutaric acid, and a diptic acid. To help you remember those names, there's actually a mnemonic called "Oh my such good apples." Okay, so oxalic O, malonic my, such, succinic, good, glutaric, and a diptic is our apples. Okay, so continuing on nomenclature, if we have a ring and the carboxylic acid is pendant to it, we name the ring first, and then we add the word carboxylic acid. So in this case here, we have a ring, and so we have a total of 6 carbons in our ring, so that's cyclohexane. But we have a double bond here. So we have to denote where the first carbon in that double bond is, making sure that we start our number where our namesake is. So our carboxylic acid is our namesake, so that turns it into our number 1 carbon. So the first carbon of our double bond is on the 2 carbon, so we have 2 cyclohexene carboxylic acid right here. If we have multiple carboxylic acids on there, we just do di, tri, tetra on here. So in this case, we have our core ring is a cyclopentane right here. And so we start with one of them and we go to the smallest number. So it'd be 1, 2, 3, not 1, 2, 3, 4. That would give us a larger number, so we're not going to use those numbers. We're going to use the shorter number. So that gives us the 1,3-cyclopentane dicarboxylic acid. And if we look at the stereochemistry of those, one of those is facing up, one of those is facing down. That gives us the trans stereoisomer of our material. So our final name is trans 1,3-cyclopentane dicarboxylic acid. Okay. So when we have a carboxylic acid pendant to a benzene ring, we call that benzoic acid. It's the simplest of our aromatic carboxylic acids. And then we start naming that as our parent again, and then we start naming whatever substituents are on here. So in this case right here, we have benzoic acid and we have a hydroxyl group and it's 1 carbon over. So that's 2-hydroxybenzoic acid. This happens to have a common name as well. It's called salicylic acid, and it's the core for aspirin, which is acetylsalicylic acid. So you have an acid acetyl group on this oxygen right here. Now, you can also have dicarboxylic acids in your benzene rings, and we would call those also dicarboxylic acids. So we'd have benzene dicarboxylic acid, and then you put the numbers just figuring out how far they're spaced apart. So in this case, you have the 1,2 benzene dicarboxylic acid. Here you have the 1,4 benzene dicarboxylic acid. And they, of course, have common names as well. And this one happens to be called phthalic acid, and this is terephthalic acid. Okay. So when we talk about the IUPAC names, we use numbers, but occasionally there's a common way to name them in which we use the Greek letters alpha, beta, gamma. So in IUPAC, we always start the number 1 with the carbonyl carbon is our number 1. However, when we look at common names, we actually start with the one next to the carboxylic acid as our alpha carbon, then our beta, our gamma, and our delta here. So if we were to name this in its common name, we would name it for 1, 2, 3, 4 carbons, so that would be butanoic acid. But it's on the 1, 2, 3 or alpha, beta, gamma carbon. So we'd call this 4-amino butyric acid, where the IUPAC name, gamma amino butyric acid, the common name would be 4-amino butanoic acid. Okay, so the butyric is the common name, therefore we have to name it with the Greek letter gamma and the substituent. Now we can also do the same thing when we have a ketone group nearby, okay? For example, the common names for things that are like this would be the acetone would be the core of this compound. Then this would be acetic acid. And so we'd call that acetoacetic acid. So it's acetone acetic acid. That's the common name. For our IUPAC name, we have to figure out how many carbons we have total, 1, 2, 3, 4, and we have a carbonyl on our 3 carbons, so that makes it 3-oxo-butanoic acid is our UPAC name, but the common name is acetoacetic acid, okay? Also, what's also very common is to have a small group on the side. This is occasionally called the acetyl group or the aceto group. This is a common pendant to a lot of things, and so you'll see that a lot in some of the more widely used chemicals. Okay, so now let's talk about the physical properties. The driving force on the physical properties for all carboxylic acids is the fact that they hydrogen bond, okay? It helps with their boiling point, it helps with their solubility, and it helps with how they react, okay? So in both liquids and solids, they do form a dimer, or one carboxylic acid is hydrogen bonding to the other carboxylic acid in kind of a head to tail fashion. So the acid of this side is bonding to the carbonyl of this side. The acid of this side is bonding to the carbonyl of that side. And so this driving force is what makes them have high boiling points, etc. Okay? So not only does it drive the fact that they have higher melting points and boiling points because of this strong hydrogen bonding, it also makes them more soluble than alcohols, ethers, and aldehydes and ketones at the same molecular weight. We have so much more hydrogen bonding available to it with the carbonyl and the OH group that you can pull in a greater number of carbons so that you can have higher molecular weight materials still dissolve in water. Okay. And so part of that has to do with the idea that they have this very, very polar head, which is where the hydrogen bonding takes place. But then the rest of the thing, the rest of the substrate here is what we call a hydrophobic tail, or that non-polar tail. So what we'll see when we use these again and again is that at a certain number of carbons, which is approximately 6, the hydrogen bonding alone will pull it in. But then after they get longer than that, you have to start making them salts to pull them into the system. And you might recognize this as something that we see a lot in the biological systems. As this chain gets longer and longer and becomes more hydrophobic, we tend to call them fatty acids because they have that non-polar hydrocarbon-like tail and then that carboxylic acid portion of it.